Alright, so in this video I'm going to be going through the June 2014 Unit 1 paper. So let's get started with some particle physics. So we've got a K plus particle has a strangeness of +1. What is the quark structure? So a strangeness of +1 means it's got an anti-strange quark in it. That would give it a charge of +1/3, so we need to add 2/3, which means the other quark must be an up quark to give us a total charge of +1 and a strangeness of +1. What's the baryon number of the K plus? Well, it's not a baryon, so it's going to be 0. It's a meson. What's the antiparticle of K plus? Well, has same particle but opposite charge, and incidentally this would be made of an anti-up strange like this, and you can see it's the opposite quarks as well. A K plus may decay into a neutrino and an anti-muon in the following way. Complete the table using ticks and crosses as indicated in the first row. So charged particle, well, K plus is clearly charged. Muon neutrino is not. The clue is in the name neutrino. Whereas muon, well, that's an anti-muon actually, is positively charged. Is a hadron, that is none of them. What am I talking about? That's absolute rubbish. This one is a meson, which absolutely is a hadron. I'm being a ninny. These two are leptons, however, so they are not. And K plus is also a meson. These two are both leptons, so they can't be mesons. Okay, so fairly straightforward once you stop being a wally. In this decay, charge, energy, and momentum are conserved. Give another quantity that is conserved and one that's not conserved. Baryon number, if it exists as a reaction, baryon number must be conserved. However, we're going from strange particles to not strange, so we're not conserving strangeness, which means it must be a weak decay, because if you're not going to conserve strangeness, it must be weak. Okay, so let's continue on. Another possible decay of K plus is shown with the following: K plus to pi plus plus x. Identify x by ticking one box in the following list. So looking at this equation here, baryon number to start with is 0. Baryon number of pi plus is 0, so it can't be a baryon. So let's get rid of any baryons. So that means it can't be a neutrino. Cross means it's not, by the way. So we can get rid of that one straight away. On the left, we've got no leptons. And you can see we've got no lepton here, so we can't have a lepton either. So that one's out, that one's out, that one's out, that one's out. That eliminated quite a few, so we're down to 2. And it's positively charged to start with, and it's currently got a positive charge of +1 afterwards, so X must be neutral, which eliminates the negative pion. So we're left with, it can only be this one, a neutral pion, so we can just eliminate them there. Okay, so the reason for the choice, so it just says for 1, so because it must be neutral to conserve charge. We can also say it can't be a baryon or it can't be a lepton to conserve baryon number. All of those apply, but that's the simplest one, so let's go with that one. Alright, so that completes question 1. Okay, so the next question, we've got a table of data about 4 different nuclei, and we've got the numbers of neutrons and the nucleon number. So I've added in some columns to this table. I've added in a column for the number of protons each has, because that's the difference between these two numbers. And I've also calculated the ratio of proton number to nucleon number, because that gives us an idea of the specific charge, which is going to come up in a minute. Okay, so let's put that to work. So which contains the fewest protons? Well, we can see here, this one here does, so that's Q. Which two are isotopes of the same element? Well, which two have the same number of protons? That's P and R, so those are your isotopes. State and explain which nucleus has the smallest specific charge. So if we look at the values we've got here, you can clearly see this one is the smallest ratio of protons to nucleons, so that's R. And if you think about how a specific charge is calculated, on the top line you'd have proton number times the charge of a proton. On the bottom line you'd have nucleon number times mass of a nucleon. So you can see the ratio of protons to nucleons gives you the ratio of the specific charge. So that's what tells you. So it's clearly R. Complete the following equation to represent beta minus decay. So beta minus decay, you're going to emit a electron, which has its charge of -1, but a nucleon number of 0. We're also going to emit an anti-electron neutrino, which has nothing for either, to conserve electron-lepton number. And then what we can see here is we've increased the number of protons, so that will be 7, but in beta minus decay, a neutron turns into a proton, nucleon number doesn't change, so that's still 14 there. Okay, so then let's continue on. The strong force is responsible for keeping protons and neutrons bound in a nucleus. Describe how a strong nuclear force between nucleons varies with the separation of nucleons, quoting suitable values. So this is a question that comes up every couple of years or so. So I'm just going to turn sideways and sketch this because there's not really enough space. So the general graph looks like this. This is repulsive, this is attractive, and then these happen at set values, these crossover points. So the first thing is this first part of your graph here, where it's repulsive. So let's put that. So when separation is less than 0.5 femtometers, strong force is repulsive. So let's get that down. So that's the first stage there. Between 0.5 and around 3 to 4, it's attractive, and it has a maximum around 2 femtometers or so. And then, so let's get that one. So it's not a precise value, it is between 3 and 4 femtometers, somewhere around there. And then finally, after 3 to 4 femtometers, there is no force at all. So those are the 3 stages, so those are the 3 marks for this question. Okay, so let's carry on. Let's move that along with it. Okay, so another significant interaction exists between protons in the nucleus of an atom. Name this interaction and name the exchange particle responsible for this. So it says a significant interaction, so it's not going to be gravity because that has a very small effect. So the interaction is going to be the electromagnetic because they are charged. That will be your interaction, and their exchange particle is a virtual photon. So-called virtual because it doesn't actually exist, it's just a way of modelling it, but we won't worry about that too much. Okay, so that completes question 2. Let's move on. Okay, so next question is looking at what phenomenon can we use to demonstrate the wave properties of electrons? It's an electron diffraction experiment. So diffraction is a wave property. It's not one that can be explained by particle theory. So if you can make something diffract, it's behaving like a wave. Calculate the wavelengths of electrons traveling at a speed of 2.5 times 10 to the 5. So this is the de Broglie wavelength, h over mv. So Planck's constant we can grab from your formula sheet. And 934. Frankly, if you haven't memorized it by now, that's a little bit ridiculous. You should have. And mass of an electron, likewise, you should have used this so many times that it just comes spilling out of your head like it does from mine. Times by the speed. And then if we put this into Yoli calculator, we come out with a value of 2.9 times 10 to the minus Oh, blimey, that did not go well. Let's try that again. -9 meters, which is a similar order of magnitude to the size of an atom. An atom's about 10 to the minus 10, so it's about 10 times the size of an atom, give or take. Okay, so that's that one. So we've got some muons now with the same wavelength, but the 207 times the mass, but you want the speed. So if they're the same wavelength, essentially what we can do is we can equate λ1 to λ2, which means h over m1 v1 is equal to h over m2 v2. You can cancel Planck's constant. So we wanted the velocity of a muon is going to be the mass of the muon, the mass, the electron, velocity of the electron, and that's 207 divided by the velocity, which was what, 2.5 times sum of the 5. Actually, I was wondering, something seemed a bit wrong with that. That's actually going to be the reciprocal of the answer. That's why something seemed a bit wrong. 207 divided by 2.5 times 10 to the power 5. 1 divided by answer gives you 2 times 10 to the 3. So in terms of what I'm doing there, I realized I'd rearranged the equation wrong, and actually that equation should be of that form, which is why I then flipped it. So rearrange your equation better than I have there, but that's now correct. Okay, so that finishes that question. The fluorescent tube is filled with mercury vapor at low pressure. So, okay, we've got some quantum energy level stuff coming up. After mercury atoms have been excited, they emit photons. First of all, what part of the spectrum are they in? They are in the UV. That's just something you have to remember about fluorescent bulbs. What is meant by an excited mercury atom is when an electron has gone from ground state to a higher energy state inside the atom. So let's get that there. So an orbital electron ground state has gained energy and moved up to a higher energy level. Okay, so that's your excited state right there. How do they actually become excited? This is excitation due to electron collision. So an incident electron collides with the orbital electron and it transfers its kinetic energy to it. That's where the energy comes from. Transferring its kinetic energy to the orbital electron. I always imagine it like your orbital electron is basically just kind of like sitting there. Instant electron comes in, gives it a whack, moves to a higher energy level. That's kind of what is going on in my head there. Why do the excited mercury atoms emit photons of characteristic frequencies? So I'm going to draw myself a diagram to think about what that looks like. So in any atom, you've got these energy levels. This is ground state, 2, 3, 4, all the way up to ionized energy state up here. So let's say we've got an electron that's currently be excited to here. What it's going to do is it's going to de-excite. It might take this path, might take that one, might take this one. It might just jump all the way down. But whatever it's doing, it's got to take these fixed paths, and that's why we get these fixed or characteristics frequencies. So let's put that into words. So first of all, we can see mercury electrons have distinct energy levels. Okay, so that's what we've got first there. Mercury atoms have fixed energy levels, meaning electrons can only make fixed energy changes. So they can only make these fixed transitions. They can't go like halfway, 3/4 of the way, anything like that. They can only make fixed transitions. And that means photons emitted have to have fixed energy. That's what we've got there. So photons emitted can only have certain energies, and we've got this equation here, E equals HF. So essentially they can only have certain frequencies. Okay, and that finishes off your explanation why you get fixed frequencies, or wavelengths would also be relevant there as well. Okay, so let's do the calculation part of this question. Okay, so the wavelength of some photons emitted is 254 nanometers. Calculate frequency. So you have the wave equation, but with the speed of light because it's photons. So frequency is going to be the speed divided by the wavelength. So 3.00 times 10 to the 8 divided by 254 times 10 to the minus 9. Calculate that. 254 times 10 to the minus 9 gives us 1.2 times 10 to the 15. Actually, we can give that to three significant figures because both numbers are 1.18 times 10 to the 15 hertz. That's your frequency there. Okay, calculate the energy of these photons in the electron volts. So energy is Planck's constant times frequency. So let's calculate that first in joules. I wish I'd kept this stored in my calculator. Let's just recalculate the frequency. All right, that's your frequency times 6.63 times 10 to the power of minus 34 is 7.83 times 10 to the minus 19. And because of that order of magnitude, you can already see it makes sense to give that as electron volts. And that's joules. And that's equal to divided by 1.6 times 10 to the minus 19 gives you 4.89 electron volts there. Okay, so let's continue on. This is a fairly lengthy question. Last part. Explain how the coating on the inside of a fluorescent tube emits visible light. So the first thing it does is the coating absorbs the UV photons. So that's the first part. And then what happens is it de-excites, giving off lower energy or lower frequency or longer wavelength photons when it cascades down the energy levels. Okay, so that's what we've got there. So just to explain what's going on here, if we imagine this is like the coating, mercury emits UV, so UV causes Xi up to this level, and cascading down the energy levels is this process here where it's taking these smaller transitions. I mean, it will be taking all of these different routes, but that's the process of cascading down the energy levels. And you can see here we get these lower energy, longer wavelength electrons formed when that happens. Okay, so that concludes that question. Let's move on to some circuitry. Okay, so we've got a student investigates how the power dissipated in variable resistor Y varies as resistance is altered. This is actually a really interesting investigation to do, especially if those of you who enjoy your further maths, because you can actually derive the graph that's produced here by doing a bit of differentiation by parts, which is always fun, but I digress. Let's stay focused. So we've got the circuit they're going to use. We've got the EMF, the internal resistance, and your variable resistance. Okay, and this is the graph obtained when the resistance is varied from 0.5 to 6.5. So let's identify a few key features that might be necessary here. Okay, so we've got like a maximum power of 3 when the resistance is 3. Okay, let's go. Okay, so describe how the power dissipated in Y varies as the resistance is increased from 0.5 to 6.5. So the first thing that happens is power increases to a max value, and as I said, that's 3 watts at R equals 3 ohms. Then what happens is then power decreases as resistance increases. So those are the two stages there. So the mark scheme for this question didn't actually require you to be that specific, but I always say that if you can be specific, you should be, because you never know when another year where they might be like, well, why weren't they specific? So be nice and specific there. You'll never miss out. You've got your EMF 6 and the resistance 0.8. Use the data from figure 2 to calculate the current through the battery. So what we're going to do is we're going to go onto the graph, go to R equals 0.8 and read off the power, and then use P equals IV. So power when Y is 0.8, the power I think is about 1.95 watts, like reading between the squares. So that's the power dissipated by the external resistor. So P equals I squared R. So to get I, we need to square root P over R, which means current is square root of 1.95 over 0.8. So let's calculate what that is. 1.95 divided by 0.8 square root 1.6 amps, I reckon. Okay, so that gives us our current. So then what we want to do next is work out the potential difference. So this is where Ohm's law comes in if you want to know the potential difference across something. So we know the current, so I've got 1.56 times by 0.8 gives you 1.2 volts there. Okay. Calculate the internal resistance of the battery. So we can calculate the potential difference across the internal resistance, because we know the EMF supplied is 6. We know the potential difference across the resistor is 1.2. So we know the potential difference across this is going to be 4.8. We know the current through it is this 1.56. So R is V over I. So it's 4.8 divided by 1.56. So let's do that. Divided by answer, which I think gives a value of 3.1 ohms. Alright, so that's your internal resistance. Let's carry on. Okay, so the student repeats the experiment with a battery of the same EMF but negligible internal resistance. State and explain how you would now expect power dissipated to vary as the resistance changes between the same values. So let's think about what that circuit now looks like. Essentially, it looks like this. It's a bit rough. So you can see that actually we're supplying a fixed EMF to this. So if you think the power is going to be the EMF squared divided by the resistance. So that's the power dissipated by the resistor. We can see that because there's the only component, the potential difference is going to be the EMF all the time. So we can see that as resistance increases, power dissipated is going to decrease. So that's stating what would happen. Ugh, I hate this pen. Power would decrease. That's what would happen. So the potential difference stays the same. So essentially what I'm going to do is use the equation we've got at the bottom. P equals V squared over R is the general equation, is the potential difference across it divided by the resistance. So as R increases, I'm going to dot the symbols here because I'm getting very frustrated with my pen. So as R increases, we can clearly see power decreases there. Hopefully that now makes sense, and it's because it's no longer a potential divider. We've just got one component, so its potential difference is always going to be the EMF. Okay, so let's move on to question 6. So we've got a critical temperature of tin is minus 269. Resistivity increases as its temperature rises from this value. That's a typical PTC resistor. Define resistivity. So let's think of an equation to calculate it, then we can put it into words. Resistance times by area divided by length. So that's why you can see it has a unit of ohm meters there once we do that. So we know we've got the right equation. So essentially it's going to be the product of resistance and cross-sectional area divided by the length of the conductor. So that's what your resistivity is. You usually would define resistance, but why not? State the significance of the critical temperature. So below this temperature, material resistivity is 0. That's what makes it. It's a property of a superconductor. That's where critical temperature comes in. A sample of tin in the form of a cylinder of diameter 1 mm and length 4.8 mm has resistance 0.7. Calculate resistivity. So we're going to be using this equation we had earlier. A over L. It's going to be resistance pi d squared over 4L. So let's do that. So we've got 0.7 times by pi times by 0.001 because it's millimeters divided by 4 times 4.8, which gives you 1.1. Was that 1.1 times 10 to the minus 7 ohm meters, which is the unit of resistivity. Okay, so that finishes question 6. Let's go on to the final question. So in this question, I'm guessing we're going to have a longer answer question because we haven't had one yet. So we've got a potential divider circuit with a thermistor to determine temperature. Data has to be obtained so that a graph can be plotted to show how the reading on the voltmeter varies as temperature changes between 0 and 100 degrees. Design an experiment using the circuit to gather enough data to plot that graph. You want to know the measurements to be taken, the details of how temperature of the thermistor can be varied, an explanation of why we need the other resistor, and an explanation of how the thermistor can be used to measure the temperature of the room. Okay, so let's just take this point by point before I start writing out my answer. So the measurements we're going to need to take is we're going to need potential difference, and we're going to want repeat readings of that. And we're also going to want to measure temperature using a thermometer. So we're going to measure potential difference with a voltmeter, temperature with a thermometer. Those are the measurements. We're going to vary the temperature, so we need between 0 and 100 degrees. So we're going to need ice for the lower temperatures and then like a water bath for the hotter temperatures. That gives us nice controlled conditions. Resistor R is going to be in the circuit to keep the current very low, so the resistor, the thermistor and the resistor themselves aren't heating up and changing the temperature. And then, so once we've done that, what we'll have is a graph of potential difference, against temperature, and then what we can do is we can put that thermistor in something we don't know, and by reading the potential difference, we can read off the graph what the temperature is. That's the general idea. So we can put that into words. So to start off with, let's do the measurements we're going to take. All right, so those are the measurements you're going to take. So now we're going to use a water bath to give us high temperatures and ice to give us low temperatures. That's what we've got there. So that's how we're going to achieve the different temperatures. So a few things we're going to need to put in place. So we're going to want how the temperature can be recorded. So that's the general idea, but what we're going to do is we're going to make sure the thermistor and the water bath are at the same temperature. So we're going to need to leave it to settle, and we can stir it to speed up that process. So that's what we've got there. We've got at each temperature, allow time for the thermistor to equal that of the water bath, so that we know that when we measure the temperature of the water bath, we're measuring the temperature of the thermistor. So then next part, so why have we got an external resistor? To keep the current low, to stop the thermistor heating up by itself. Okay, and when I say preventing thermistor temperature change, I mean that in the sense of changing unexpectedly. Obviously, we want it to change as part of the experiment, but we want it to change predictably. So what we're going to do is we're going to plot a graph of voltmeter versus temperature, producing what's called a calibration curve. Producing a calibration curve. Oh, blimey, that really doesn't look like calibration, does it? Let's rub that out a little bit. Let's try it again. Okay, that looks better. That T is still suspect. Anyway, so we've got our calibration curve, and then we can use that calibration curve to measure temperature with voltmeter readings. From voltmeter readings. God, this pen is getting worse and worse. Okay, just about struggled to the end. I hope by listening to me you can work out what that's saying. Oh my goodness me, that does not look like voltmeter readings. Let's try that again. The rest of it I can deal with, but this I just can't. Okay, so I'm just going to read over that again because I'm not convinced anyone can read that. So you're going to use the calibration curve to measure, that really doesn't look like measure, does it? But to measure the temperature from the voltmeter readings. That's how you'll actually use it as a thermometer. Okay, so let's hurriedly go on to the next question. Okay, so the experiment is repeated with the voltmeter connected across R instead. State and explain how the readings on the voltmeter would be different. So as temperature increases, thermistor resistance would increase, meaning the circuit current would decrease. That's my first thing. Okay, so there we've got it in words. So as temperature increases, resistance of the thermistor decreases, so the current going around the circuit increases. And what that means is using V equals IR, as temperature increases, we know that the voltmeter reading is now going to increase there. Is going to increase, whereas before, as temperature increases, you'd expect the voltmeter reading to decrease. This is the opposite effect. Whereas temperature increased, the voltmeter reading would decrease because essentially a smaller resistance would demand a smaller chunk of the potential differences, and the potential difference across the thermistor must add together to give a fixed value there. So that completes the question paper. I apologise as always for the horrendous handwriting at a few parts, but that can't be helped, I'm afraid. If there's anything that's not clear, please do feel free to comment and I can clear things up. If you spot any mistakes, please do let me know. But as always, thank you very much for watching, and do keep your eye out for further videos in this series.